Does everyone remember that? How we found the variance of an estimator? Okay. Apparently, no one. So you should revisit those things. You should not come to the class not prepared at all. All right. So today we are going to discuss again this thing, the variance of an estimator. Okay. So as I mentioned previously, this has to do with the statistical error, or statistical uncertainty, you might say, uh, in your estimation of a parameter. And what we did was that first find ln max, ln of L max. So you, basically, how did you find it? You first found the log likelihood function. So first uh, find the log likelihood function. Okay, so you denoted this thing by log of capital L. Okay, then you find the location of the maxima, the location of the maximum of log likelihood. So ln L max. Okay, and this gives you the estimate, the ML, the maximum likelihood estimate for the parameter. Recall the parameter to be theta. And then in the last step, okay, so and this ML estimate we denoted by theta hat ML. Okay. Then the last thing you wanted to do was that from this ln L max, you go to the contour of ln L max minus half. Okay, so this contour, so this contour gives you the 1 sigma region uh, for uh, the estimate. Okay, so these were the steps, and you verified it using exponential distribution, right? Does everyone remember that? So you did this exercise as a homework, okay? And you checked. All right. So now today my job will be to discuss to find this 1 sigma region, as somebody asked in the last class. Why did I do this minus 1/2? Why did I need to drop by this half from the maximum of the log likelihood function to get my 1 sigma region for that estimate? So the answer lies in the theory, in a particular branch of mathematics called the information theory of probability. So without getting into the details, of course I'm not an expert on this information theory, so I just learned what I needed to learn. There is an identity. By the way, is anyone waiting in the lobby? Okay, there is no one. So there is an identity in the information theory that is called the RCF inequality. So uh, it's it, it goes by the name of the Rao, Kramer, and Fresher. Okay. So this is Rao, Kramer, Fresher in bound. Okay. Sometimes in brief it's called the RCF bound. All right. So it tells you. Uh, Remember, our job is to figure out uh, with how much confidence, or how, like what amount of confidence should I have on my maximum likelihood estimate. Okay, so basically you have found a value of the maximum likelihood estimate from a single set of measurements, right? So you have done a measurement of x1, x2, blah 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 up to xn. So basically, you have a data vector which is x1, x2 to xn. There are n independent measurements, and each of these are independent measurements, and each of these, suppose, are distributed according to a function called fx theta. This is the PDF. And since after n measurements you have this pattern, then from this pattern you have to guess what is my best bet, what is my best bet for this theta. And you just concluded that this theta hat ml is the your best bet for theta. So that was the statement of the problem. Now, uh, so the statistical error reflects that how robust is this estimate. So it, you are asking this question, that how robust is this estimate uh, against, uh, let's say, repeated measurements, repeated experiments. Okay. So what I want to ask is that, suppose I want to repeat my experiments. That is, suppose this is one set of x1, x2, blah 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 to xn, and then you are going to repeat this thing. So you, suppose you measure it, then your friend comes on, then the friend of his friend comes on. So they have all different sets. They have all measured independently, and they will probably have a different estimate for this theta hat ml, because theta hat ml is an implicit function of this x1, x2, this. And since your data can be different if you repeat this experiment, so this estimate can be different. So you have to quantify, if you repeat this experiment, how different this theta hat ml, the value of theta hat ml, can be. And that is reflected by the statistical error in that estimate. And for that, so to kind of have an idea of that, we did those tricks. So we first found from ln L max, then we dropped by half, and we say that this is kind of the 1 sigma region in a Gaussian interpretation that gives me the interval within which the theta hat values will lie at 68% of the time. Sorry, is somebody saying something?
Yes, I also on.
Yeah, tell me.
I think Rashi is trying to join the class.
Okay. Yeah, I have just let her in. All right. Okay, so again, so we will come to that. And to so how can we estimate this 1 sigma statistical error? So for that, I'm now going to discuss this RCF bound. Now, what does this RCF bound says? So this RCF bound says that mm, there is a lower limit on the variance of the estimator. So this RCF bound, the essential concept is that, uh, so it tells you that there is a, a lower limit, hmm, to the variance of an estimator. Okay, under uh, some general assumptions. Okay, under some general assumptions. Hmm. So there are two keywords that you should note here. So it has a keyword which is called, there is a lower limit to the variance. Suppose you have constructed an estimator, suppose this particular one, and by some method, maybe analytical method, the way we got the variance of the exponential estimator, the lifetime of a decay. So that estimator we constructed, which was just the arithmetic mean. So for that estimator, you already had calculated the variance for that estimator. Okay. Now you might wonder, remember, one of the one of the ideals that you want to achieve in constructing an estimator is that it should have a minimum of variance, that minimum of statistical error. Remember, I talked about the sampling distribution and some points. So this g theta had given theta, and you wanted the distribution to be narrow, so that under repetition of experiment, you can be very confident that the whoever repeats this experiment again, that person, he or she will not get a value that is much different than that what you have already quoted. So that can only be achieved if your variance is small. Now you have constructed a thing and that has a variance. Now you wonder, could I have done better? Could I have come up with another variance, another statistic or another estimator, form of an estimator, which will have a lower variance than the current one. Okay. Now, if you know this theorem, this RCF bound, it tells you no matter what no matter what estimator you can cook up, you can construct, there is always a lower limit, and this lower limit is valid under some general conditions. So it's not like you are imposing some special restriction and only then this is valid. It is valid under some general assumption and conditions. So you can be very confident that whatever test statistic or whatever form of estimator you could have come up with, that will have a lower limit on the variance. Okay. Now, suppose, so you know that lower limit. I will tell you how to calculate that lower limit. Now, suppose that you have constructed an estimator and for which the variance is already close to the lower limit that you know from this theorem, then you can automatically decide that, okay, my search ends there. Okay, so as long as the statistical error is concerned, I cannot construct anything better. So that is kind of the first hint that you can get. So how good um, is your estimator? So one way to reflect on that will be to compare the variance of that estimator with this lower limit that is given by the RCF bound. Okay. Now, uh, now let us move on to the actual statement of this RCF inequality. So it tells you. So let me first give you the theorem. So the theorem is this. All right. So let x1 dot 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 up to xn, okay, be sampled from some PDF, okay, from some PDF that I denote by f of x given theta, uh, with theta being a parameter. Oops. And here the note should be that this xi, so this xi's are independent and identically distributed. So here let me put that is. Okay, so no, my eraser is a bit too big. Parameter, that is xi's are independent and are identically distributed. Okay. So we choose an now estimator. So we choose an no, how can I change the stroke? Cannot change it here. Anyways, I have to do it later. We choose an estimator. So that is given by theta hat, which is a function of the data for theta with bias. So there is the definition of this bias. So I call it B theta. So of course this bias depend on the definition of theta hat. So it depends on this theta hat. So I put this subscript theta hat, and it is in general a function of theta. So I will often drop this subscript, but in your head you should remember that the definition of the bias, uh, by definition, it depends on the structure of this theta hat. Okay, so the bias will be different for different estimator, which is kind of a given. So this is the expectation value of this theta hat minus theta. Okay, so this is the bias and the finite variance and finite variance. So the variance I denote by uh, v theta. Okay. So the variance is finite for all theta. Okay. So now then the RCF inequality tells you that this the variance of this theta should be greater than equals to uh, 1 plus del b del theta, where the this b is the same b here. Okay, I just dropped this thing, drop the subscript. So 1 by 1 plus del b del theta whole square divided by I theta. Okay, now so I am assuming this for a single parameter theta. Of course, this PDF can depend on multiple parameters. Let's say theta 1, theta 2, theta 3. Then this inequality will be slightly modified, and we can intuitively guess how it will modify. So I will come to that later. But for a single variable, for a single parameter theta, this is it. Okay. So this I theta, whatever I have introduced here, this this I theta is called the Fisher information number. So this is called the Fisher information number. Okay, and this is given by the expectation value of this del theta summation over k equals 1 to n uh, logarithm
Uh,
of,
Fred?
yes,
Sorry to interrupt. Rashi, I think she is saying she cannot join. No.
she cannot join. uh, I,
She is
I
saying,
I already allowed her, right?
yeah, but I do not know. She is saying that she cannot join.
Mm, okay, I will make you then the co-host so that you can allow people if they want to join. Okay,
Okay.
yeah, all right. Uh, so this is my Fisher information number. Okay, now of course at this stage it is not very clear how this will be useful at all. But let us try to understand how this such a complicated thing came to be. So remember this variance of this theta. So this is so this is essentially the statistical error. Okay. Now this is, I call it sigma theta square. So that is the variance of theta hat. So without proving this, I will come to the proof in a moment. But if this is true, then you notice that this sigma theta squared, the standard deviation of this theta hat is greater than equal to something. So this gives you a limit. So this bias is this bias is known for some particular value of theta hat or particular structure of theta hat, and this information thing, it's an expectation value that only depends on theta, so that can be calculated as well since you know the distribution. Okay, so you can check what is the upper bound on this theta hat. Of course, the right hand side might depend on the true value of the parameter theta. So in that case, you replace the true value of the parameter theta by your estimate, and you can have a have an idea about how big this variance of theta hat can be. Now, if you hit that limit, then essentially you can say that okay, you have chanced upon, or you have guessed a very good structure for the estimator, and that can do your job. All right. Now, let me come to the proof. Before I go to the proof, there is a short name for this del theta f theta kind of thing, which is sometimes called the score function. So I might use it. So these are common terms in the information theory if somebody is interested in that. Okay. So this Sx theta, which is written as the del theta of log of f uh, x theta. Okay. So this is called the score function. The score function of a distribution. All right. It will be useful in certain cases. Okay. So, but if you still cannot find the connection to the maximum likelihood, look at this thing. So this is precisely the log likelihood thing, right? This or this. So this will later be connected with the likelihood analysis. That's the ultimate goal. But let us forget about likelihood analysis now. Let us focus on this particular theorem and try to understand how can we proceed to prove that thing. All right. So we will assume that this fx theta is a continuous distribution. We will not talk about discrete distribution so much here, but if we can prove it for a continuous distribution, the discrete distribution can be proved likewise. So first we notice this thing. Okay. So suppose you have a test statistic or a function tx, then if we have this, so let's say result number one. Result number one. What I want to say is that suppose you want to calculate this del theta of expectation value of tx, right? So integration tx. So tx is some function of x, tx fx theta dx. So what you are doing, so this is basically the thing inside this green bracket is the expectation value of tx, right? Now, this um, this can depend on theta. This expectation value can depend on theta because the distribution itself depends on theta. So I can legally take derivative with respect to theta here. So this expectation value of t can do this thing. But I notice this thing, this tx does not have any dependence on theta. So the theta dependence is only contained here. And it is very often possible to interchange the order of differentiation and integration in certain cases, if this can be done. And in most of the cases, it can be done as well. So this is, so I will assume that this holds. We can interchange that order of differentiation and integration. Since the differentiation is acting on a different variable than the integration, so it is likely that it will hold. Yeah. So since the differentiation acts only on theta, there is del theta operator. So it will treat this dx as a constant thing, and it will only act on this fx theta, and this times dx. Pretty obvious. Now, on the spatial case, if I go to the spatial case, So this special case with dx equals 1. Then if I substitute it here, then on the left hand side I have del theta, then just integration of fx theta dx, this. That should be equals to integration of del theta f x theta dx. Alrighty. And on the left hand side, this is just expectation value of 1. Remember, this differentiation was a valid operation because it was in general a function of theta. It is in general a function of theta, but it need not be a function of theta always. A special case is this. This is the integration of the PDF itself over the whole sample space, over the whole span of dx. So this thing is 1. Things inside the bracket is just 1. Okay. This comes from the normalization of the PDF. Okay, so del theta operating on 1 is 0. So that means this integration of del theta fx theta dx is 0. So this is my result number 1. So this integration del theta f of x theta dx equals 0. So this is my first result, first boxy thing that I conclude. Then using this, we can draw certain corollaries. So the first corollary we move towards is this. So the expectation value then, the expectation value of del theta log of fx theta. Okay. So this is, so remember this is nothing but the score function. Okay, so this is sx theta. So this is the, according to the definition, this sx theta is this. So I'm trying to get the expectation of the score function here. So this is equivalent to the expectation value of s x given theta. Okay. So how do I do that? So the expectation value of anything is basically that particular thing, which is del theta log of f x theta. So this thing times the distribution function, that is f x theta dx. Okay, this is my thing. All right. Now del theta of log of fx theta. Okay, which is, so if you take the del theta of log of anything, first thing that comes out is that 1 by that thing. So log of fx theta, you take the derivative, so 1 by fx theta, because log, and then del theta of fx theta. Okay, this times this fx theta dx. So first thing I notice is that this cancels in the numerator and the denominator, and you are left with this del theta fx theta and dx, and that by my first box is 0. Okay, so the expectation value of the score function is 0. So this thing is equals to 0. That is my second result. So the expectation value of del theta log fx theta is again 0. Okay. So now if I uh, calculate this thing, so let me write this thing. So therefore, okay, the expectation value of the del theta of summation over k uh, log of f. Now we are slowly moving towards the likelihood thing. Okay. So if I calculate, this is a very complicated thing, so take time to fathom a bit. So this is the summation over k log of fx k theta del theta. So it's basically sum of all the score functions, okay, of for all these for all the values, this x1 x2 x thing. So the sum of the score functions, and their square. Okay, so the s1 plus s2 plus blah 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 square. Okay, so first thing you can do is obviously you can take the derivative uh, of the derivative inside the summation. So what you have is this is equivalent to the expectation value of summation over k del theta. So as I told you, is the sum of all the score function sk theta whole square. Okay. So consider this as x square, okay, whatever that is. So suppose I call it mm, say x square. Okay, call this thing as x. Now, if you remember the definition of variance, okay, so suppose the variance of x is basically expectation value of x square minus expectation value of x, that is that's whole square. Okay, so this is the theorem, or this is the definition that I'm going to use here. So consider this as your x, capital X, in the place of this. So I have expectation value of x square here. I have this term here. This term is this. So I can write this term as the variance of x plus expectation value of this thing whole square. Now, notice carefully again. So first I write this is the variance of summation over k del theta. So that thing again. So x is that thing. Uh, ln f xk given theta plus the expectation value of summation over k uh, del theta. So the expectation value of x, I will put x inside. So this is del theta ln f xk theta bracket close, and then the whole thing whole square. All right. Now remember, this is the expectation value of a sum. That means that would be sum of the expectation values, right? So this is the sum of all the expectation values. But I have already found out, so the sum of all the expectation values of all the score functions. But I have already found out that the expectation value of the individual score functions are zero. So this, because of this, okay, here, this is zero. So this is zero because the expectation value of the score function is zero. This is zero. Okay, so this goes away. All right. So you are left with this. Now, this is the variance of the sum of these things. So variance of the sum. So variance is first and this sum in the second. Now, if my random variables are independent, which these xk's are, then variance of the sum is just as same as the sum of the variances. So suppose, so I ask you to prove this. So suppose you have two random variable, let's say x1 and x2, and then you have to prove that if x1 and x2 are independent, then the variance of the sum v of x1 plus v of x1 plus x2 is equals to v of x1 plus v of x2. Okay, so the variance of the sum is basically sum of the variances. All right, so that means I can take this summation symbol outside. So this is given as like variance of the sum, and I can rewrite it as the sum of the variances. So sum of the uh, variances. So this k equals 1 to n v of del theta uh, ln f xk theta. Yeah, so this becomes the sum of the variances. Now, since all my random variables are identically distributed, this x1, x2, x3, these are all identically distributed. So that means the variance of any individual one will be the same. Okay, in terms of theta, they will be the same. Okay. So I can just calculate the variance of the score function. So inside this, you have the score function, by the way. So this is the sum of the variances of the individual score functions. Since the xk's are identically distributed, so the score functions will be identically distributed as well. So since all of them are identical, this I can write is as the n times the variance of the individual source score function, like any individual score function, which is del theta ln f x given theta. Okay. So this is the third result, is the expectation value of the score function square is this. All right. Now, so this result I will be using in a moment. Okay. Now, another thing, so far I have not talked about the test statistic or the estimator itself. Okay. Now, suppose I want to calculate the expectation value of the of this quantity. So similarly, what I can write down here is this. So the expectation value of this is theta hat. This is the estimator I have constructed. So theta hat, remember, I will not write it here explicitly because it will be too clumsy, but remember it has x1, x2, blah, 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 and the arguments as well, times del theta summation over k ln f xk given theta. Okay. So I have to calculate the expectation value of this thing, and I am doing it purposefully actually. So remember, so theta hat. So all the x1, x2, xn are involved in many different ways. So I have to take the joint PDF, and the joint PDF, since the x1, x2, x3 are all independent and identically distributed, joint PDF is just the product of all the individual distribution. Okay, so this expectation value should turn out to be like this. This should be equals to integration. So there are multiple integration depending on dx1, dx2, so on. There is this theta hat. So theta hat has an argument x1, x2, blah blah blah. Then you have this core function. Okay, so del theta. Here I will play a trick here. So I will take the summation inside. So summation of all the logs is basically equals to log of the products. Okay. So this del theta times log, I take the log outside, then the summation, if it goes through the log, it becomes product, because this. So the log of the product, so the pi is the product symbol here, then fxk theta, this. So this is the function, times the joint PDF. The joint PDF is just the product of the distribution. So uh, this this is the product symbol pi j, and then f of xj given theta dxj. Sorry, I don't have space. So this is my joint PDF. Okay, if anybody is confused, so this is my joint PDF. Now this is it. All right. So now del theta of log of this. How do I do this? So I will apply the same trick as before. So whenever I am taking the derivative of a logarithm, whatever is in the argument of the logarithm comes in the denominator, and the del theta of the rest. Okay. So let me write my next step. So there are this is the multiple integrals over x1, x2, and so on. This is theta hat. Notice this derivative carefully. So first of all, this thing comes in the denominator. So 1 by uh, by k f x k theta, alrighty. Then del del theta, I use another dummy index, let's say pi of I, f of xi theta. Okay, so this is my del theta. All right, so this is the whole derivative, and then the joint PDF is pi j f x j theta dxj. All right. Yes.
नोटबुक कौन सी वाली चाहिए आपको?
Uh,
प्लेन या लाइनिंग वाला?
Plain. Uh-huh.
इसमें लाइनिंग है।
Uh-huh.
आप प्लेन
So if you notice then that again in this denominator this thing and this thing cancels out, and we are then left with a rather simple thing. Okay, so so then this is equals again the double integral theta hat, then there is this del theta, and then the product. So the product I will open now up. So this is f x1 theta blah 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 up to f xn theta. Okay, so the derivative of all these products and times dx1 up to dxn. Alrighty. Okay. So if I take this del theta out, because this theta hat only depends on x1, x2, xn. Okay. So let me write it down. This thing depends on x1 blah blah up to xn. So this del theta does not act on this theta hat because it has dependence on data, not on the parameter theta. Okay, so you can safely take it out of the integration sign to write down. So this should be equals to del theta times the integration. Okay, then theta hat, then times the product fx1 theta la 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 fxn theta la la la. Now you again notice that this product is the joint PDF, right? It's nothing but the joint PDF. Now, of course, I am multiplying this joint PDF. Sorry, not up to dxn, dxn up to dxn should end here. It's a mistake. All right. So this theta hat is a function of x1, x2, x3, and so on, and I am multiplying it by the joint PDF of x1, x2 to xn, and I'm integrating it over. So this thing without the derivative, this integration is nothing but the expectation value of theta hat. So this integration within these brackets is the expectation value of theta hat. All right. Now, if you remember the definition of the bias, so the bias of an estimator is the expectation value of theta hat minus theta. So this expectation value of theta hat is just b theta plus theta. Okay. So this thing is nothing but b theta plus theta. Right. So this del theta, when operates on this, it will simply give you del b del theta plus 1. Alrighty. So this the expectation. So this is another result. The expectation value of this theta hat times the score function is just del b del theta plus 1. Okay. Now we are almost towards the end. Okay. To get this bound, okay, hold on a second. Let me get some water. All right. So to get the final bound, what I need to construct is the covariance matrix. So the covariance matrix of the two quantities, the score function again and the theta hat. How do the covariance matrix look like? All right. So now I construct. Uh, so first I notice that the theta hat xi and uh, the quantity um, summation over k uh, del. So this is the sum over the score functions log of f x k theta. Okay, these are both random variables. Why? Because they have always involved this k here, xk here. Since xk are itself random variable, so this function is also a random variable, and so is this estimator. It is also a random variable. Now we want to understand if these two are correlated, and so that uh, we can we can get some information about them. Okay, so let us construct the covariance between these two. So the covariance of this summation over k del theta log of f x k theta comma theta hat xi. So the covariance of these two quantities. So remember the definition of covariance. If you have forgotten the definition of covariance, so the covariance of two random variables, that's x and y, are given by the expectation value of xy minus the expectation value of x times the expectation value of y. So these are the covariance. Okay. So if x and y are completely independent, then the covariance would be 0. Okay. So now, if these are so, if I can want to calculate this, then I have to first do expectation value of xy. So the expectation value, the product of this thing. Okay. So first this quantity summation over k del theta log of f x k theta times theta hat xi, expectation value of this, minus the product of the expectation value of the individual quantities. So minus the expectation value of summation over k del theta log of f x k theta, okay, times expectation value of theta hat. Now this can be anything. This is related to the bias, but this is the expectation value of some of the score functions. Okay, but the individual score function, the expectation value of the individual score function, they always vanish. So this is 0, right? So this thing is 0. So this term drops out. The second term drops out, and we have already computed this thing. So this is 1 plus del v del theta. We just computed the product of the expectation value of the product of these two things, right? So in the yellow, this is the product of the expectation value of these two things, precisely these two things, right? And that came out to be 1 plus del v del theta. So this covariance thing, I can conclude. So this is again 1 plus del v del theta. All right. Okay. So you can now construct the correlation matrix. So from covariance to correlation. So from covariance to correlation. So how do you get the correlation? You just divide it by the individual variances. Okay. So and take the square root. So if I do not take the square root, then I will have rho square. Okay. So this is the covariance of this thing. So first of all, I have covariance of these two quantities, summation over k del theta log of f xk theta comma theta hat xi. So the covariance of these two things whole square divided by the variances, right? You go back and check on the definition of the correlation function. Okay, so this is the variance of this thing. So the variance of the individual ones, the variance of the score function. First of all, p of del theta log uh, f xk theta times v theta hat. All right. So this is my correlation matrix. Now, I think I gave you an exercise to calculate covariance and correlation. Remember, the covariance can be anything. The minimum value can be 0. But correlation magnitude wise can be within 1, within 0 and 1. Okay. So if they are perfectly correlated, then the correlation is 1. If they are not correlated at all, then the correlation is 0. And like in between, it oscillates between 0 and 1 if there are like the degree that they are correlated can be indicated by a number between 0 to 1. Okay, so this quantity, this rho square that I defined here is just the correlation. It must be less than equals 1. This quantity is less than equals to 1. Alrighty. So then of course you see that v theta is sitting here. So something divided by v theta is less than equals to 1. That means v theta should be greater than equals to something. So that enables me to write down. So if I take v theta over here, then variance of this theta hat, all right, this should be greater than equals to this ratio. This is the covariance of whatever in here. I am not writing it again. So whole square divided by the variance of this thing. So the variance uh, of the score function. All right. The summation over k del theta log f xk theta. Now the thing on the top, I have already pointed out that this covariance is 1 plus del b del theta whole square. Okay, so this v of theta hat is greater than equals to, in the numerator you have 1 plus del b del theta whole square divided by the variance of the score function. And the variance of the score function, we have seen it somewhere. Okay. So I think this is the variance of the score function. All right. So this is the variance of the score function, which is sitting in the denominator, and that is equals to the expectation value of this expectation value of the score function square. So I'm just going to write that. Okay. So this divided by the expectation value of the score function. This is summation over k del theta ln f xk given theta, okay, whole square bracket close. Okay, and this is the RCF inequality that we started to prove, right? Where is that? Here. Okay, this is the thing that we started to prove here, and we have essentially proved that. But this proof, or rather this particular result in this particular form, is not very useful for our maximum likelihood analysis. So for that, what I will do is this basically manipulate this expression a bit and try to get it in a nicer form. So first, remember this result. So this is my, first result in today's class. And now I'm going to manipulate this result to kind of make it conform to our use in the context of maximum likelihood analysis. Okay. And at the end of the day, so remember all these things, all the exercise, albeit it might be a bit boring because you don't enjoy information theory. I mean, I am not an expert on that, but it's good to have an idea of other fields sometimes so that you get a better understanding of the things that you are handling. So if you are using likelihood and you are doing, so I intend to do that. So to write this in a form that is more useful to our cause, I want to go beyond this thing, and I want to check that there is an interesting way of translating this expectation value below into something that is more directly recognizable. Okay, so our goal is to convert this into something uh, directly recognizable. All right. So for that, at least we proceed to uh, figure out what is this thing. So this is del 2 over del theta 2. This is summation over k ln f x k theta. Okay. So this thing, this is again the del 2, this is the second derivative of the sum of the score functions, not the score functions, sorry. Second derivative of the sum of the logarithm of the distribution. And to do that, I write this is as del 2 del theta 2. This is then log of the product. So this is log of pi k f of x k theta. And same old trick. So there are two del theta. So this del theta and del theta. So I keep one del theta outside and operate the other del theta to get the desired thing. So this is 1 divided by the product. So this is pi k f x k theta times del theta operating on the product. So I use a different index here so that I do not confuse with the other index. This is xl theta. All right. So now bracket close. Now I am going to operate this again. Okay. So now there are two functions. So this is function number 1, and this whole thing is function number 2. So this del theta will operate on both. Okay. So first, quite clearly, if I operate on this on the first function, so it will operate on this. So this is 1 over x something. So 1 over something. So this is minus of 1 over x square. If you operate del x on 1 over x, you get minus 1 over x square times del theta operating on this thing, which is the same as this. All right. So again, when it operates on the first, watch very carefully what I write here. So the first term is minus 1 over x squared, which is minus of 1 divided by the product pi k f x k theta whole square. Alrighty. Then del theta operating on this thing, which is the same as this thing. So it's basically this thing's whole square. This is del theta operating on pi over pi on L f xl given theta whole square. This is the first thing. The second is it does not affect the first term and it only affects the second term. So this is just plus 1 divided by the product. This is the pi k f x k theta, and then del 2 del theta 2 operating on the other thing. So this is del 2 del theta 2 operating on the other thing, which is essentially the same pi fxl theta. Good. So I just take this square and this square together, and I can just write this is del theta log of this whole square. So the first two terms can be put together to write down this is del theta log. So this square and this square put together. So inside there is just 1 by fx theta and del theta of that theta. So this is del theta of logarithm of the whole thing. All right. So this is again verify it yourself. So this is del theta operating on the logarithm of the product of f xk theta, the whole thing square, and then the next thing is plus 1 over the product pi k f xk theta, and then that is del 2 over del theta 2, then pi over L f xl operating on theta. So this is just this, just carried forward. Okay. Now let us convert this into something more recognizable. So take this product outside of the logarithm to write it as the sum. So then it becomes the sum of the score function. All right. So this is minus of summation over k is the sum of the score function. This is the del theta ln f xk theta whole square, plus again the same thing carried forward, 1 divided by pi k f xk theta del 2 over del theta 2, and then the product of all the distribution all over again. So this is it. All right. So this is what? This is the left hand side. So this del 2 del theta 2 is this. Now what I am going to do is that I'm going to take the expectation value of the both side. So take expectation value of this. So expectation value of this thing. So remember now expectation value of this thing should be equals to the expectation value of this thing plus the expectation value of this thing. So I will clean this thing up. I will clean this thing up. So now so the expectation value of this del 2 del theta 2, this is summation over k log of f xk theta. All right. So this is equals minus of expectation value of the summation over k del theta log of f xk given theta whole square plus the expectation value of all those things, right? Now when I write the expectation value of all those things, notice what happens. The second term, the expectation value of this term, focus on this term. So the expectation value will be, so try to do it in your mind. So that's for the second term, the expectation value. So integration, you have all these joint integrations you want. Then you have 1 over pi k f xk theta. Then you have del 2 del theta 2, same product, pi L f of xl theta. All right. And then the joint PDF. So this is the function whose expectation value are needed. And then the joint PDF, which is nothing but the fx1 theta dot 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 up to fxn theta times dx1 up to dxn. First thing we notice is that this joint PDF precisely cancels this denominator again. Okay. Now this del 2 del theta 2, it operates on this, and this integration is only on x's. So this del 2 on del theta 2 can be taken out. So you can move it here, the del 2 and theta 2. Then the inside is basically, again, the joint PDF times all the integration variable, which is, because of the normalization of the distribution function, is basically 1. You take the derivative of 1 with respect to theta, you get 0. So this thing is 0. So this expectation value is nothing but this expectation value. Now, in the identity in the RCF inequality that I proved so far, it involved this expectation value. Remember, this is the expectation value I have. Okay, this is the square of the score function. Now, because of this identity, I can convert this expectation value into this, the negative of this. So using this, the way you can write your RCF inequality, so the final form of the inequality that I will be using is V theta hat, all right, should be greater than equals to minus of, minus because of this sign, 1 plus del V del theta whole square divided by the expectation value of del 2 del theta 2, then summation over k ln f of xk theta. All right. So that is the form that we are going to use. So this is my usable form of RCF, okay, of RCF bound. Now again, if you are looking very carefully, then this summation over k, this summation over k log f x k theta, this is nothing but your log likelihood function. So this is log of the likelihood function. Okay. This is how I defined my likelihood function, which you wanted to maximize. Okay. So using this then, so this then reduces to V of theta hat should be greater than equals to minus of 1 plus del B del theta whole square divided by expectation value of del to L, or rather del to log of L, del to log of L del theta 2. This is the form. Now you see the connection with log likelihood. Okay, now what? Now there will be two practical assumptions that are very often satisfied. Okay. Although they seem a bit off uh, for now, but they are usually satisfied. So first of all, assumptions that we will involve now. Number one, the bias is small and can be neglected. Okay, so this is my first assumption. You have seen that the estimators that we have constructed very often have zero bias. Okay, so the what I mean is that del v del theta will be ignored. This term will be ignored. And number two, which might be a bit counterintuitive uh, to you for now, and it is also very like usually satisfied that this inequality to the inequality can often be replaced by an approximate equality. Okay. So these are satisfied in practical scenarios. I'll tell you how. So using if you put these assumption into this, then what comes out is this. So this v theta hat, which is the statistical error, okay, should be approximately equals to minus 1 over expectation value of del 2 ln L del theta 2. That's it, nothing else. Okay. Now you might wonder, how do I know that like what I am doing is correct? Like how did I, to what degree should I trust this assumption? So for that, I strongly advise that you should go back to the exponential distribution. So example, let's say. So this exponential distribution, for which I gave you a homework. So this is uh, f t given tau was just 1 by tau e to the power minus t by tau, and you found out that the log likelihood function, so ln L, which is the function of the parameter tau, which is summation over I equals 1 to n. Uh, this is ln 1 over tau minus ti over tau. Okay, so this is my log likelihood function that you have found out. And then after doing the maximum likelihood, so you maximized it to find that my maximum likelihood estimator for the lifetime for tau is 1 over n summation over I ti. Okay, so this is just the arithmetic average, and this was indeed, so this estimator, the maximum likelihood estimator that you got was indeed a zero bias estimator, because it's just the arithmetic mean. Okay, and the arithmetic mean had zero bias. Okay, so this had zero bias. So assumption number one checks out. Now again, in the analytic way, when we said that we calculated the variance of this tau ml, so uh, we in using analytic method, we had previously calculated that the variance of this estimator, so the variance of tau maximum likelihood, is just tau square over n, where n is the number of data that you have. And I use this to illustrate that the more number of samples you have, the more data you have, x1, x2, blah, 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 to xn, the more confident you can be in your measurements. And you explicitly verified that just by generating 100 points and generating 1,000 points, that the errors comes out to be proportionately low. So this is the expression of the variance that we already know and we have learned to believe. Now I want to check whether I can obtain the same expression for variance for this exponential distribution using this RCF inequality, and then when I convert it to equality, does it conform to my expectation for the analytical thing. Okay, so I already have the expression for log likelihood. What I have to do then, so remember this is del 2 ln L del theta 2. So you take the double derivative of logarithm of likelihood with respect to the parameter of interest and find it out and check the expectation value of that. So let us do that. So using this expression, of course, if you proceed on calculating del 2 ln L del tau 2, then you will end up with, I have uh, done this previously, so I'm just copying from my notebook. So this is n over tau square 1 minus 2 over tau times 1 over n, summation over I ti. Okay, so this part, the last part, is nothing but the maximum likelihood estimator for tau. So this is n by tau square 1 minus 2 by tau, then tau maximum likelihood estimator. That's it. So now if I calculate the expectation value of this, so the expectation value of del 2 ln L del tau 2 will be n by tau square. Expectation value of 1 is just 1 minus 2 by tau. Expectation value of tau ml hat. Since this tau ml hat is a zero bias estimator, so the expectation value of the estimator is the true value itself. So this is 2 by tau times tau, which you have seen. So then it just is 1 minus 2, and this is minus n over tau square. So if I substitute this, so expectation value of del 2 ln del tau 2 is minus n over tau square. You see, you might be wondering that this minus sign, this variance of theta hat, why this minus sign is here? That is because since you are maximizing your log likelihood, so at some point your log likelihood is maximum, so its double derivative will come out to be negative, right? Because at a maxima, uh, the double derivative is negative. That's the rule. So to get a positive variance, this minus signs make sense, and this is what you have seen, right? The double derivative around that maxima is negative. So if you substitute that here, then you get this variance of tau ml should be minus of 1 divided by minus n by tau square over n. So this again conforms to our usual expectation. So this assumption that this can indeed be reflected as a as a equality also holds true. Okay, so this is it. So this del 2 ln L del tau to this thing. So I can confidently write now. So I can confidently write that v of theta hat, which is equivalent to sigma of theta hat square, that is equals to minus of 1 by expectation value of del 2 ln L del theta 2. All right. Now, so then, so then how did I actually obtain this variance from here? So the actual variance was given by, then, so this is the variance. So the variance still have the true parameter in it, but by definition I do not know the true parameter. I have to find out an estimate of the variance. So what I can do, instead of using this expectation value, so since this is tau square over n. So instead of using the expectation value here, I just calculate del 2 ln L del theta 2 at the maximum point, at the maxima, and I call that is my variance, because from here, from the analytic computation, what we did was that the estimate for the variance, so this is the variance, okay, which I never know, but the estimate for it, again, the hat is here, the hat is on the V as well. So that is, again, you put tau ml square over n. So how did we get that? So we basically evaluated this del 2 L and del tau 2 at the maximum point and then got it. Okay. So if I want to have the V hat theta hat, which is equivalent to sigma hat theta hat square. So remember, this is the variance, actual variance of the theta hat, and this is the estimate for the variance of theta hat, and that can be given by minus of 1 over, instead of taking the expectation value, I just calculate the del 2 ln L del theta 2 and evaluate it at theta equals theta hat ml, and that's my that should be my sigma hat theta hat square. Okay, so I can invert this equation. So this essentially implies that del 2 ln L del theta 2 evaluated at theta equals theta hat ml should be given by minus 1 by sigma hat theta hat square. All right, this is the relation that I finally got. Now it is quite straightforward to see what happens if I plot log of L theta. So you have the log likelihood, right? So the log of L theta that you have found out, that you have learned to learn. You can expand it in a Taylor series around the maximum likelihood value. So this log likelihood has a maxima at some point, and in the neighborhood of that maximum, what you are doing is you are expanding around it. So first you get log of L at the maximum likelihood point. Then of course the first derivative, this is del of ln L del theta evaluated at theta equals theta hat ml times theta minus theta hat ml, alrighty, plus the second derivative 1 over factorial 2 del 2 ln L del theta 2 evaluated at theta equals theta hat ml theta minus theta hat ml whole square plus higher order terms. So first thing you notice is that this term is 0, because by definition at theta maximum likelihood, this is the maxima, so the first derivative is 0, and this is my ln L max, right? So in the second line I write, so this is my ln L max, what you have got, the maximum likelihood, minus theta minus theta hat ml whole square divided by 2. So remember, this thing, this del 2 ln L del theta 2 is just 1 over sigma theta square. So I am just replacing, that's why the minus sign. This is sigma hat theta hat ml square. Okay, this is it. So if I try to plot now ln L theta, so it will have at theta equals theta ml, you have ln L max, and then it's kind of a parabolic shape. The parabola will be more pronounced the more data you have. For a smaller amount of data, you will not have this thing. So suppose you went out and plot this ln L theta. The nature of plot you have. So suppose in this direction you have theta. You have this kind of parabolic plot. So this is your theta equals theta hat ml, right? So that is your maximum likelihood. And the nature of the function is uh, like it's ln L max minus some positive quantity. Since this is a square, this is a perfect square, it's a positive quantity. So it falls on both sides. No matter if you overshoot theta from theta ml or you undershoot theta from theta ml. So on both sides, it falls down. Okay. Now, so of course, then this value correspond to, so this is my ln L max. So now if I go to these values, so suppose use this. I'm looking at theta equals theta ml hat plus minus sigma hat theta ml hat. So if I put this value for theta, then of course theta minus theta ml is equals plus minus sigma hat theta hat ml. At these values of theta, what is the value of my log L theta? So I can take it from here. So since this is plus minus theta ml, so the square will be just theta ml square. So at these values of theta, I will have log of L theta will be log of L max minus, since theta minus theta ml is plus minus sigma, so you put it here, sigma square cancel out, and you are left with half. So as long as you are away from theta hat ml, the maximum likelihood value, by 1 sigma, so this is, suppose this distance is sigma theta hat ml, whatever the statistical error that I defined to be, and in this way as well, so this is the distance of sigma hat theta l, then whatever value it gives you here, so this value over here would be ln L max minus half. So you plot the log likelihood and you find the maxima, and where you drop by half, you are within 1 sigma of this thing. All right. Now what happens if there are multiple variables? So suppose you have two variables, let's say theta and theta 2. Then this plot will be a three-dimensional plot. Try to imagine this thing. Then this thing is definitely a three-dimensional plot. So you have what you have is theta 1 and theta 2 here. So suppose there are two parameters, theta 1 and theta 2. Okay. And on the axis that is perpendicularly above to this plane of the paper, you have this ln L, that is a function of theta 1 and theta 2. And it will be a maximum somewhere. So suppose at this point, that thing is maximum. Okay. You do a contour plot if you want, okay, maximum. And that gives you the maximum likelihood values of this theta 1 and theta 2. So this is theta 1 ml, theta 2 ml. That is the best fit value. And to find the 1 sigma confidence region, so you have to find the contour. So this should be the contour in which, so the contour in the theta 1, theta 2 plane. Where the ln L is basically ln L max minus half. And that should be the 1 sigma region. So the meaning of this 1 sigma in short is that under repetition of this random experiment, that means again you measure and your friend measure, like hundreds of people measure independently, they repeat this experiment. By the experiment I mean collecting all the data together, like collecting x1 up to xn, all this together, and do it thousands of time, millions of time, and every time if you do an estimate The maximum likelihood estimate, every time it will be different. But using a Gaussian equation, 68% of the time, the best fit value will lie within this region. So that's the 1 sigma confidence interval in one way. If the errors are Gaussian, which in the most case it is. Okay. So that is how using likelihood analysis, first of all, you are able to figure out the best fit value of an unknown parameter, and on top of that you can also estimate the statistical error or the degree of trust that I should have on that particular best fit value from the log likelihood analysis. Okay, so I think I will end today's lecture here. Sorry, this was a quite long and things, and these things will take time for you to follow. But I strongly recommend, if you want to understand likelihood and these things, you must learn these things. I mean, well, I had to learn, and I am not a statistician by any means. So, well, so I will close here, and let me know if you have questions on today's class.
Sir, when you told about these assumptions, you told like bias is small, then how curly beta by, sorry, curly b by curly theta is zero?
Um, all right, because usually the bias is zero. Okay, so and bias is usually independent of theta as well, and bias is small. And if it remains small for all values of theta, then the bias is not varying with theta so much. So
Okay. Okay. Means expectation value of our this estimator is equal to that parameter.
yes,
Okay,
very
okay.
close to the parameter.
Okay, sir. Okay, thank you.
Mm,
Sir,
yeah.
sir, while calculating v hat theta hat, okay, so we didn't take the expectation value of del 2L and del theta 2. Why did we do that?
uh, to calculate v hat theta hat.
Yes, sir. So we
I No,
yeah.
because no, for v hat theta hat I did not take the expectation value.
Why,
For
sir?
v theta hat I took the
Yes,
expectation
yes,
value.
yes.
Okay. See, v hat theta hat is the estimate for the variance. Okay. So I connected it from our earlier exercise on the exponential distribution. So you see, using analytic method, we found that the variance of this estimator is tau square over n. Now this tau is the true value of the parameter, which I never know, which we do not know. Then what can be the approximate value or best guess or a best estimate for this variance? So we can say, okay, I can replace this tau by the my best fit value tau hat ml. So what did I do? I calculated my variance by some mean, by some other way, and then replaced the parametric value there that I can calculate, that I can maximize it. So here, if I do the same trick, since this is my v hat, and I already calculated del 2 L and del theta 2, right? Yes. So this is my estimate del 2 L and del tau 2, right? Now, if you replace tau with tau hat ml, okay, in this expression, right? You can
Yes.
see it, right?
Yes, yes.
So then you get basically, so if basically what I mean is that suppose you take this rule as the estimate for the variance. Suppose this assume this rule for the estimate of the for the variance, and you check it for the exponential distribution, like starting from here. Okay, it works.
Okay, sir.
Okay, right. Anything else? Okay, if not, then I will stop recording, and I will see you next time.